My talk is going to be pretty fast and a lot of information, but without going deep. I mean, about new developments in machine learning that brought some mathematical theories, and what Enrique was talking about is a part of these new developments and new paradigms in machine learning, which I will try to explain as fast as possible. Sorry, just so which I will try to explain, and then of course if any questions. So this is the outline, but we will not make it through the whole slides. So let's say that, just briefly say that neural networks are an old idea. So they started from 40. So you have an input layer and then some set of hidden layers, and then you have an output. So neural network is an architecture that consists of several layers, and each layer consists of several neurons, and neurons are functions f. So you have this idea that started, for instance, this was called cybernetics in all times. So they started in 40s, study of neural networks and so on. So in 58 there was famous perception network. So in 60s there was some decline of interest because there was some criticism because neural networks really couldn't do what people expected. So in 80s again there was a rise of interest. There was this paradigm of connectionism, and then in 80s they started this backpropagation method for training neural networks. So, but then again, decline of interest. So machine learning was dominated by ideas of support vector machines, graphical models, different graphical models, and so on. And finally, starting from the paper of Geoffrey Hinton about deep belief networks in 06, there was a growth of interest that tries to explosion. And so now neural networks are, neural networks are getting bigger and bigger. They are getting huge, and the interest in neural networks is very high. So Geoffrey Hinton is one very influential mathematician who made a lot of contributions, whose impact is huge. He is Englishman working in Toronto for the almost whole career. So he made a lot of important contributions and papers about different aspects of Boltzmann machines, neural networks, and so on. So very good book about this is over here. Good fellow Benjo Kurvil, Deep Learning. There is a book. So something from this talk I took from this book, but this is like, but I'll talk about some my ideas and some conceptual ideas. So renaissance of neural networks in 21st century and emergence of deep learning. So neural networks are getting bigger and bigger and bigger and very big, and number of layers is like millions of layers here, or you can have thousands or even millions of layers. So, and the depth, the number of layers is called the depth of neural network. So they are getting extremely deep neural networks, so many layers. That brought the new paradigm of deep learning. So, okay, how do we train neural networks? We need to train them. What is the training of neural networks? It is process of optimization essentially. We are looking for optimal synapses here. We start with a certain architecture with certain values of these weights, synapses, and then we train the network by optimizing the values of these synapses. So, okay, so what do we, for instance, the goal is to minimize some function like something like quadratic error or something. Let's say this kind of function, you have experimental data and you try to update these weights, these synapses. So you try to update them in order to get better value of the expected of quadratic, for instance, error. So this is L is the loss function, F okay, f here is the expected output, so LL is loss function, for instance, quadratic function, quadratic error, and this is empirical. We are minimizing mathematical expectation of the error with respect to empirical data. So, but the parameters of the problem, I mean, we minimize with respect to theta. Theta denotes all weights in the network. So we are really creating the network. Okay, and this is really optimization problem. So we initiate some weights, and then we need some optimization algorithm to optimize these weights theta. So we make a step through the network from the input to the output. This is propagation forward. And then we get some value of this function of this function L, and then we have calculated the error. We need some optimization technique to improve the weights theta. I mean, to optimize this. This is we are going back from output to the input through the layers, and this is called back propagation. So we train networks through back propagation, and back propagation is an optimizing algorithm of optimization, which can be, for instance, gradient descent or stochastic gradient descent, which can be some of these very well-known traditional optimization methods. So these are methods of numerical optimization. Or these first five are based on the gradient. You know, we go down the gradient essentially. Or we can have some gradient-free optimization methods like evolutionary algorithms, or for instance, some stochastic search algorithms. Okay, this is not important. Okay, and then sampling, I skip this. Okay, also mathematics important. What is important is the methods for sampling from the neural network, because we use some Monte Carlo techniques from through the big network. So, for instance, the main technique here is Monte Carlo Markov chain technique, but there is also this Gibbs sampling, which is from statistical physics. Idea is purely from statistical physics. So the whole time we are doing some sampling, calculate, and then optimize the network. So this is the method. This is the main idea. So how does it work in practice? So neural network, let's say it is a mapping F. So this is Y is output, X is input. So this is the mapping that depends on the input and weights theta. So, and this is composition of many mappings. So composition of really many of n mappings, and n is really high number. So F are these layer maps, F1, F2, Fn. There are so many of them. So, and the whole neural network is a composition of n mappings where n is really large. What is so, for instance, you can have linear mappings, but you know, of course, you would like to work with some relatively simple mappings. For instance, linear mapping, but of course this doesn't work, because if you have linear mappings, composition of linear maps is again linear maps, so you can get only very poor expressive power. You can have only linear map in the end. So of course you must have some non-linear maps. Okay, and then you choose these maps which are which must be, some of them must be non-linear, otherwise you have very poor expressive power, and optimize. So for differentiation, for the calculation of the gradient, you go backward, back propagation. As I say, you go backwards, but you use the chain rule essentially of differentiation. So I ask people who are doing this, well, if you have this chain rule for so many layers, for so many functions, you must calculate, you must have some error, and this error is getting bigger and bigger, and I think it cannot work with millions of layers or with even thousands of layers. But it works because these functions, these layers are very simple. There are linear functions, linear mappings, or very, very simple nonlinear mappings like ReLU, as Enrique said. So these are essentially piecewise linear mappings, like ReLU, the simplest possible nonlinearities. And so it is quite easy to differentiate linear function or piecewise linear function. So this ReLU function. So this is how it works. There is no error in differentiation. So for instance, this is, I would say, the most typical practical approach to building neural network. So in 15 years, there is maybe this approach is good, maybe it is not, but now they have a huge infrastructure. They have libraries mainly in Python, in C, in whatever these Python. So there is a huge infrastructure. They use it in practice. And so it takes a lot of time to make this, to build this infrastructure. And so this is now the dominant idea in neural networks. So that's it. And this I told about practical deep learning here. And so, but there is now a field, they call it scientific machine learning, where you are talking about machine learning from a scientific point of view. So this would, one might say that this is a new branch of mathematics, very challenging and very interesting one, because theoretically and potentially you have so many applications of mathematics here, so that the perspective is very, so mathematics here in deep learning is potentially extremely powerful and extremely rich. Like, and we saw only a small part of it in, for instance, in Enrique's talk. So let's say we have one idea about neural networks, how to introduce these ODEs and PDEs as something that Enrique was exploiting, this idea. So we have residual neural network. So this is the scheme. Essentially, this residual architecture provides this this iterative method, but this is essentially only just the Euler scheme for the, this is essentially discretization Euler scheme for the following PDEs, ODEs. So if we take a very small step, infinitesimally small step, and we divide it by this step, and then we say, okay, this is essentially, we get ODE. So we can use ODE instead of these. So if we have many smaller steps, we have more layers, more and more, and we have infimum of layers, continuum of layers. So we have ODE as an approximation of neural network, or neural network is an approximation of ODE, discretization. So let's take a look at the neural network as a dynamical system, as continuous time dynamical system. So for instance, this researcher Wayne and E worked a lot, contributed a lot. He's from Princeton, and he, from this theoretical point of view, that neural networks are dynamical systems. And so you have these continuous time dynamical systems, and you have all the control theory. You have a rich control theory about these dynamical systems. And you can construct and build neural networks through as ODEs. So, and how about training such neural networks? So again, we have some parameters theta here. So how do we learn these parameters? How do we, they are analog of synapses in this neural network that I explained above. So how do we train it? Well, we can say this is a control function. This theta is control function, and it can be constant. It can depend on the time. So this is control function, and then we have to minimize something with respect to this control function theta, and this is optimal control problem. So can we solve? Do we know how to solve optimal control problems? Yes, we have a rich theory. We have many methods. We have numerical methods for optimal control problems. So maybe this could be advantageous. This continuous time approach maybe could be, for some purposes, it could be even better than traditional. So, and how to implement backpropagation? I mean, this Well, this is done, for instance, this is given by, for instance, Pontryagin maximum principle. So backpropagation is essentially a joint equation in Pontryagin maximum principle. You can find such an equation, which is a joint equation, which is linear ordinary differential equation, goes backward in time. So, and essentially by solving this equation, you are doing backpropagation. So, in the theory, sorry. Sorry, just small technical problem. So in ODE theory, a joint equation, you can find it, for instance, in the theorem about a joint sensitivity method. So if you want to check how sensitive is the solution of ODE with respect to the variation of parameters, you will get this adjoint, linear adjoint. And also you can find, of course, it appears in Pontryagin maximum principle, which is the solution. Its solution is this adjoint function is a Lagrange multiplier in the Hamiltonian function. So what I say is that this adjoint method is precisely backpropagation. So you have some infrastructure to treat neural networks, to do some experiments with such approach. You have libraries, mathematical libraries for ODE solvers, for numerical control theory, and all this stuff. So these 4 young people, Chen, Urbano, Betancourt, Devendu, made some experiments with this idea in 18, and they are also from Toronto. They also wrote this paper that proved to be highly influential. They introduced the concept of neural ODE. So this is not completely new concept. So many researchers previously were talking about this, but they somehow solved some toy problems. They implemented it, and this as a control problem, and they solved some. So they demonstrated how to solve some toy problems with this, and so since then there is a rising interest in this concept of neural ODE. So, and one application of this was shown just previously by Enrique. Okay. So in training neural network is a optimization. So traditionally you use these gradient methods, gradient descent method of optimization, or some improvement. But then there is another approach, especially if you want to maximize mathematical expectation, or minimize mathematical expectation, which you usually do in. So there is another approach. So to optimization, to the problem of optimization. So let's say that we want to optimize this function f of x. F depends on x. So call this function fitness, just for fun. If you don't want to work with gradients, you can employ stochastic search, implement stochastic search. So find some probability distribution that provides a maximal expected value of the fitness function. Then you can sample from this probability distribution. So for instance, you are looking this probability distribution in the class of probability distribution, which have some parameters, which depends on some parameters theta. So this is optimization problem. Very of the kind what they do in the spirit of machine learning. So the optimization problem is to find these parameters theta, so to optimize with respect to that mathematical expectation with respect to this probability distribution is maximal or minimal, doesn't matter. So for instance, you want to maximize this, then you can use so-called log likelihood trick, So to differentiate this with respect to this mathematical expectation with respect to parameters, so this function J is essentially expected fitness. What do you expect to get if you pay something, if you play some strategy? So you have this nabla, I mean gradient operator, then you just divide and you get that this this gradient of the expected fitness is essentially expectation of this. So you get this, this is called log likelihood trick. And so you have this relation, and this means that you can estimate a gradient. You can estimate the search of the gradient. So here I should have gradient. So this is gradient is the expected. So from Monte Carlo sampling, you can expect this as an average. So here I should have nabla. So there is a small mistake here, sorry, in the equation 3. But essentially, you can estimate search gradients from by using Monte Carlo method by sampling. So, and you can then implement, if you have the gradient, you can implement gradient ascent update, gradient ascent algorithm to maximize, or gradient descent to minimize, whatever. So, but okay, but this employs conventional gradient, Euclidean gradient, while we are looking to optimize our class of probability distributions. And this is not appropriate, this is wrong, because we want to appropriate over certain, we want to optimize over a certain class of probability distribution, and this is not Euclidean space. For instance, this can be, this class of probability distribution can be just categorical distribution. I mean, just distributions, probability distributions over the finite set. So this, what is this space? This is unit simplex, and this is not Euclidean space, for instance. Or let's say the family of Gaussian distributions. You have, this is also not Euclidean. This doesn't have Euclidean geometry. Because A is a mean vector, but C is not any matrix. It must be positive definite matrix. So what I'm saying that here we optimize over non-Euclidean space, and gradient descent, Euclidean gradient descent is not appropriate. We need something, for instance, to take into account this non-Euclidean geometry in the in our gradient, in our optimization method. So for instance, just to show you, so assume that you have these two random variables normally distributed with parameter. One is, this is mean value, this is variance, and this the second one. So the Euclidean distance between them is very small. If you take Euclidean distance, if you want to measure how distant they are, then if you take the Euclidean distance, you will get very small. On the other hand, you have some two normally distributed random variables with high variance, then Euclidean distance is huge, but it is very difficult to distinguish these two, and it is very easy to distinguish these two. So because of the small variance, they are very easily distinguishable. So if you have a sample from the first and second, you will immediately be able to say if it is first or second, because they have small variance. And if you have normal distributions with high variance value, then you will never distinguish them. Very, very difficult to distinguish. I mean, you need very big sample to be sure, to be fairly sure. So what I say is that these two are far apart, and these two are quite close, and these two are far apart. And Euclidean distance is not the appropriate way to measure the distance. So what is appropriate way is Kullback-Leibler divergence. This is not metric. Okay, this is not metric, but locally it is metric. It is a distance locally, because it is not metric because it's not symmetric. It's not, it is not symmetric, but locally it is. So it generates the metric through its Hessian. So this metric on the space of probability distributions is called Fisher information metric. Fisher information metric. So Fisher information metric for instance, family of probability distributions, probability measures with Fisher information metric is called statistical manifold. One example, for instance, if we consider a family of one-dimensional normal distributions, you will see with Fisher metric, it will be identified with Pontryagin disk, so hyperbolic geometry. So if you work with Gaussian, especially one-dimensional, but if you don't have Euclidean, you have hyperbolic geometry. Furthermore, so you need not gradient ascent, which takes into account the geometry, and this would be this modification. Here we put the Fisher information matrix, which depends on the family that we are working with. In some cases, you can explicitly calculate Fisher information matrix. In some cases, for some families, you cannot. For instance, for Gaussian, even multidimensional, you can explicitly calculate Fisher information matrix, so it is very convenient. So this is called natural gradient, and introduced by Amari, Shihu Amari, Japanese. So natural gradient, because, and it is related with the vanilla gradient, and vanilla gradient is just a vector of partial derivatives through this Fisher matrix. So if you maximize or minimize over the family of probability distribution, you must use this Fisher matrix. I mean, it is you can do whatever you like, but people who are using, because in many algorithms they are using just normal vanilla gradient, it can be, you can have very wrong results or very badly, I mean, collapsing algorithms. So the last thing I will, I will also, some comments about evolutionary game theory and how it works in machine learning. So evolutionary game theory, you have a game which is repeated, and players learn their mixed strategies, and they choose each time at each round, player chooses his action from a certain set of actions, and his action has a fitness function. Once the action is played, this fitness function is evaluated. So if this action brings poor results, then you decrease the probability that you will play this action again. But you don't kill. This probability is not zero. You just say, okay, I will not play this action because this time it was like you are playing, rock, scissors, paper. If you play scissors and you lose, it doesn't mean that you will never again play scissors. You just say, okay, so you somehow actions that prove to be successful have higher chances, higher probability to be played again. So have higher frequency. So the player is gradually learning the optimal probability distribution over the set of possible actions. So this is called mixed strategy in the game theory. So this is process of evolution. So gradual learning of the optimal probability distribution. And so this process is given by evolutionary dynamics, which are essentially replicator equations, which are system of ordinary differential equations. If you exclude mutations, if you include mutations, then you have some system of PDEs. So these ODEs are something in the spirit of Lotka-Volterra ODEs. If you have PDEs, if you have mutations, you have PDEs which are in the spirit of reaction diffusion equations. And so such equations play very important role in the evolutionary game theory. So in the end, for instance, just imagine that two people are playing rock, scissors, papers. In the end, they will learn, they will update their strategies, but the end, the both of them will end up with having 1/3 strategy. So they will equally frequently use three strategies, three actions: rocks, scissors, or papers. So this is how the algorithm of evolution, how we learn through mistakes. through trials, not through mistake, but by trialing. So, but essentially, and I'm currently working on this issue, replicator equations, which are ODEs, are natural gradient ascent algorithms. Very interesting that essentially you can implement these natural gradient algorithms by through the evolutionary game. You write replicator equations and you organize evolutionary game, and you will get and this is natural gradient algorithm essentially. So natural gradient is intimately related with evolution, with evolutionary games, and so evolutionary games are essentially very good, very nice tool to learn and to train neural networks, or to even to be neural network, to act as a neural network. So what are the main concepts of evolutionary game theory? Is set of you have set of actions, you have mixed strategy, you have best response, you are learning, you are maximizing fitness, you in the change in changing environment, and you have evolution. So this is exactly what should be like for training artificial intelligence. So in fact, we have it also in machine learning. This is called reinforcement learning. So evolutionary game theory is a framework of reinforcement learning, more precisely, a little bit more complicated, just multi-agent reinforcement learning. So it has been recognized that evolutionary game theory brings new paradigms to the, I mean, people are working on this because this seems like a very perspective area, that evolutionary game theory is not so complicated. It appeared as a biological, then it has some impacts on philosophy, but now it seems to be that in the future it might be the most important for deep learning, for artificial intelligence. So just about alternative, for instance, inspired by statistical physics, you can what did we have? We have natural gradient, and this is intimately related with Kullback-Leibler divergence. And here we can say, okay, and we had some statistical manifolds, this is called information geometry. An alternative approach is, for instance, free energy. You minimize it, and you want to learn these bounds. And to learn free energy, you know just that this is quadratic functions, but you don't know coefficients. So this is training of the neural network to find coefficients of free energy. So what do we have then? We have Fokker-Planck equation, essentially like average of Langevin equations, and Langevin equations are gradient, and Fokker-Planck is essentially, so you have gradient descent method over Wasserstein space. So you have Wasserstein space is the space of probability distribution with Wasserstein metric. And so if you want to implement gradient descent in this space, it is essentially Fokker-Planck equation, gradient descent of the free energy. And that's one approach. And the second approach is to use Kullback-Leibler divergence for the distance of measures. And people explore one and another approach. Many people who are strong in physics and mathematics. And of course, for designing neural networks, you can also combine these two approaches. I'm just saying that I'm currently interested in these applications of evolutionary games. So just there are some other very mathematically demanding and challenging paradigms in deep learning. So normalizing flows is what essentially Enrique had a problem with normalizing flow. So normalizing flow is something, okay, just I don't have enough time and too much information for one talk, but I just saying that Enrique was talking about normalizing flows. Essentially, it was something very similar. So normalizing flows, then you have, okay, you have variational autoencoders, also demanding mathematically, like a model of neural network that is quite successful. Then you have, okay, you have generative adversarial networks, which are based on game theory. And very interesting, you have geometric deep learning, which is working with non-Euclidean data. So most of data essentially is non-Euclidean, and we just saw one. So you need to, to learn some non-Euclidean data. If you, for instance, learn motions, rotations, some motions that if you want to learn it, this data is non-Euclidean. So you need Riemannian geometry. And here I conclude. Page down. Okay, so for scientific deep learning, what do we have? We have, what do we need? We must be good in linear algebra with optimization and probability and statistics, which includes mostly Bayesian learning. Markov chains are very important for deep learning. And recently, and it has been always necessary for machine learning previously. Recently, you have dynamical systems and control theory, which is, for instance, one instance is Neural ODE, but I agree with Enrique that control theory is very a neighboring field with machine learning. Okay, but this is not the only neighbor, but I agree. So in recent developments, you have you use all the so many things from dynamical systems and control theory. You use evolutionary game theory, especially evolutionary game theory for reinforcement learning. Then for geometric deep learning, you use Riemannian geometry, especially Lie group theory. Then you need statistical physics. You might need information geometry. I'm just telling that it is so rich field, and that you that it is very advantageous if you are good in some of these theories. All these theories are applied to deep learning, and they bring new ideas. The field is really active, evolves really rapidly, and I mean this provides new challenges for mathematicians. How it will look in the next 5 or 10 years, I don't know. I mean, artificial intelligence and machine learning, but I'm just telling that it is getting more and more mathematically demanding and demands more and more. I mean, for instance, now geometry or probability in geometry is like very good tool for some problems of machine learning, while 10 years ago, nobody thought about geometry or group theory for machine learning. I don't know. So now people from group theory are doing machine learning also, and some things like that happen. So thanks a lot. I think that's it, what I wanted to say.